Good day, everybody. This is going to be a lesson about solving a situation where we have an object going around an embankment. So it's doing circular motion on an embanked road, but I'm going to include friction. Now, in my last video, the last one that I created, I worked with this situation where there was no friction. So it's just a completely frictionless ramp. And the way I explained it was, you have to build the two force vectors, gravity and the normal force, and work out how they result in the centripetal force, because in circular motion, the only net force is that centripetal force. So Fg and Fn have to add up to Fc, so it looks something like this. And from that, we realize if that's Fg and that's Fn, that Fc must be the x component of Fn, or the horizontal component. So that was a pretty simple problem to solve. Now, when we work with friction, we have to add in another force. So that this other diagram that I've got here, actually let's slide this right out of the way, is what we want to work with. So now we have three forces netting out to that centripetal force, which means our actual diagram, when we construct it, is going to look something like this. We've got gravitational force coming downwards. The normal force has got to be bigger because friction force is also adding a downwards component. So our normal force is going to bring us up above that horizontal line, and then the friction force is going to bring us back down to the horizontal line, such that the resultant is that horizontal centripetal force. So this is a situation where the car isn't sliding up or down the ramp, but friction is contributing to the centripetal motion by pushing the car down the ramp when the car, through inertia, wants to slide up the ramp. All right? So now we've got three vectors we've got to work with. So I built this to make it a little more easy to see. I'll shrink this and keep it up in the top corner as a reference. Oh, that's not what I meant to do. But here is the vector diagram, and I'm going to group that together so I don't accidentally do what I almost did with the other one. There. Okay, it's all there. Good. So basically what we have is the three black vectors, gravity, normal, and friction forces, and they are contributing to that centripetal force. So their horizontal components will contribute to the centripetal force. So that will look like, let's do this not in blue, but in green. So the normal force, Fnx, will be part of it, and Fx will be the other part. All right, and excuse me. That's one side of things. The other thing we know is that since this object isn't sliding up or down the ramp, there's no vertical motion, no vertical action, no acceleration. So let's do these vectors in green, or red, sorry. We have gravity bringing it down, normal force bringing it up, and then the friction force bringing it down. Those three vectors have to come out to zero. So we're going to work with those two principles to figure this question out. Now, before I go any further, you'll notice that I haven't put any numbers in here. I'm not going to. There's only going to be one single numerical value in the final answer, and it's going to be a squared. Okay? The reason I'm doing that is because I want to provide you with the ability to make a flexible solution. There are 1, 2, 3, excuse me, 4 variables. 4 variables here that you need for the final answer. The one that I did not put in that diagram, I just realized it, is the coefficient of friction. Coefficient, in this case, it's static friction because the object, the car, is trying to slide, but it's not sliding. So there's no movement along that horizontal, or that plane of that embankment. Okay, so how do we start? We want to build an algebraic expression that allows us to relate those 4 values. The 4 values are mu, mu, the speed, so mu is coefficient of friction, V is the speed of the car, the tangential speed, R is the radius of the turn, and theta is the angle of the embankment. Those four variables are the only variables I want in my final solution. So here's how we start. I'm going to start with this expression here. All right. What I'm going to say is the centripetal force, Fc, is equal to Ffx plus Fnx. So the normal force in the x component, actually I'm going to reverse those because that's how I did it before and I want to follow my solution. So Fnx plus Ffx add up to my centripetal force. Now, the angles, hopefully you can see how these two thetas relate to each other, how they are the same theta. The friction force should be pretty obvious because the friction force is in the plane of the ramp, which is angled at theta from the horizontal. And we've already discussed in other problems in grade 11 why this value is theta as well, this angle is theta. So, let's expand this a little bit. We know Fnx is going to be Fn times the sine of theta because Fn is taking the angle theta from the vertical, so this one up here is the opposite, so Fn sine theta, and we know that Ffx, the friction force, we know the friction force is mu times the normal force. So we're going to say plus mu times Fn. But it's not just mu times Fn, it's the component in the x direction, which is adjacent to theta, so we're going to write cosine theta there. Next line. Now, we're looking at this and we're saying, okay, I have mu, I have theta. Those are two I'm allowed to have in my final value. But Fn, I'm not given Fn, and you're almost never going to be given Fn in a problem like this. So I've got to replace Fn. So what can I replace Fn with? Well, I have to turn to the vertical forces. All right, so I'm going to use the red stuff here, and I'm going to say that, let's see, easiest way to put it is that Fg in one direction, because this all comes out to zero, the vertical forces, is going to be equal to Fny, the magnitude, plus Ffy. Sorry, minus, I messed that up, minus Ffy. So Fny minus Ffy. Let's write that out. Fny minus Ffy. And I can play around with this a little bit because I want to solve for Fn. I'm going to, but I know that Ff involves Fn, so I have to expand a little bit and say Fn, and this time Fn is going to be cosine theta, and it's going to be minus mu times Fn, and the y component of friction is, hang on, sine of theta. So that's what I have on the right side. Now to get Fn by itself, I have to factor it out of that right side and then divide both sides by what's left in the factor, which is going to be cosine theta minus mu sine theta. I'll underline those. So if I factor Fn out, I'm going to have that left inside the brackets. So let's do that, and I'm going to divide that on both sides, which means I'm going to get Fn equals Fg divided by cos theta minus mu sine theta. So I can now put that in for my Fn on the other side. So let's come down here and say Fn is replaced by Fg over cos theta minus mu sine theta. So I'm going to say Fg sine theta, so that's what's coming down from above, the sine theta, and then it's Fg divided by cos theta minus mu sine theta. So there's my first term. My second term, mu, and then Fn I'm going to replace again with Fg over cos theta minus mu sine theta. So it's going to be Fn cos theta, that's the top, over cos theta minus mu sine theta. Okay, so now I have, mu Fg. I knew something was wrong there. Let's write that out again, just completely. So mu Fg cos theta over cos theta minus mu sine theta. Okay, there we go. So I'm going to extend the page here and continue from there. Now, what I have here, I've got theta, mu, and Fg. So, not given Fg, the force of gravity acting on the car. I told you before, we're going to solve this down to v squared, or Vr theta and mu, right? So let's do that. We have to replace Fg with mg. And here's how we end up on the right side. We've got mg sine theta. And by the way, the denominator is the same on both sides here, so we can add plus mu mg cos theta all over that common denominator of cos theta minus mu sine theta. Now, there's only a couple of little steps left, because since I'm solving for the centripetal force here, we're working with the centripetal force, I also don't know what Fc is, right? But I do know, and I'll write this over here in green again, that AC is equal to v squared over r, and therefore Fc is equal to mv squared over r. That's Newton's second law, right? So I can replace Fc with mv squared over r. So now I'm going to write on the left side mv squared over r, and on the right side mg sine theta plus mu mg cos theta all over cos theta minus mu sine theta. And there's only a little, a small step left, or a couple of small steps left, because in the end I don't care what format my equation is in. All I care about is that I have a formula that I can use to solve for any of those four variables. And what I see here is, first of all, m cancels, because every single term here has an m in it, every single term across the top. So I could factor m out on the right side and divide both sides by m, and m is gone. The second thing I can do is I can look for common factors. So g can come out because g is in both of these. So I'm going to factor g out to the front. Let's see where that leaves us. V squared over r equals g, and then basically just a fraction. Just a second while I look at my work here. I feel like I've got a minus sign in my answer down here that I shouldn't have. Yeah, I switched the plus to a minus, but I won't do it here. Sine theta plus mu cos theta. I think I've got a smartboard acting up on me here. Divided by cos theta minus mu sine theta. So look at what I've got here. Look at what I've created. I've created a formula that has only 4 variables in it. 1, 2, 3, 4. G isn't a variable unless you're planning on doing this on another planet, right? V, R, theta, and mu are my only variables here. So That's a very powerful thing to be able to do. Now, I know that anytime I have a situation where there's an embankment with friction, and it's perfect circular motion, this formula will work. If I'm given any three of those variables, I can calculate the fourth. This is what we always want to aim for when we're solving for physics problems, is an algebraic variable expression to which we can add numbers and solve for an actual numerical answer. Okay? Is there anything else that I can point out here? Not really anything significant, but let's just scroll back quickly so you can see everything we did here. Just a quick recap. Started with my vector diagram, where the gravitational force, the normal force, and the friction force add up to produce a resultant that's just the horizontal centripetal force. Then I built the horizontal expression out of the two x components of the values that have x components. Gravity doesn't have one. So gravity is not actually contributing to the centripetal motion here, which is interesting. I took that equation, let's just poke at it in red. I took that equation for the centripetal force, and I started substituting in things that I knew, like Fn sine theta for Fnx, and then finding an expression for Fn, and using that to eliminate Fn, which I don't know, and then finding an expression for Fg, and using that to eliminate Fg, which I also don't know, and then simplifying my algebraic expression to make it as easy to use as possible. Now, another thing I should point out, this might not be where you end up. That might not have been how you started this. There are a whole bunch of different ways to go through this solution. This is the one I used. I found it most efficient for me. As long as you wind up with an expression that can be rearranged to this, you're right. And that's how actually a student and I checked our answers, was he got a completely different answer from, different looking answer from me, but rearranging one, you got the other. Okay, thanks for watching.